Okay, so it's been quite a long time since I've sat here and recorded a video, but I'm going to record the 2022 VCAA exams for maths methods. For those of you also following along with the further maths / general maths videos, unfortunately I haven't taught further maths for a couple of years now, and I just don't have time to record exam solutions in a subject that is not going to be of value to my own students at the moment. So I apologise for that. I won't be adding to the general maths series this year. But I'll at least add the 2022 VCAA exam solutions. I would like to add some of the Northern Hemisphere solutions, but time's at a bit of a premium at the moment, so apologies if I don't get to those, but I'll definitely do exam 1 and exam 2 from 2022. Okay, so exam 1 from 2022. I'm also going to think about answering some of these questions in the context of the 2023 study design. In particular, there's one question on this exam that I would have answered differently last year and would have taught my students to answer differently, but that is still accessible under the new study design. We'll talk to that when we get to it. Okay, so question 1, page 1, fairly standard for exam 1, differentiation question, product or quotient rule usually. So here we have a product rule. Students often miss these product rules when it's just an x. It's easy to miss that this is actually 3x, a linear function, multiplied by, e to the 2x, an exponential function. So we are going to need our product rule here. So I've got my formula sheet to hand. So if you are not sure that you've remembered your product rule correctly, make sure you come and have a look at your product rule here. So it is leave the first function as it is, derivative of the second function, plus leave the second function as it is, derivative of the first function. Now, because you're adding those two things together, it actually doesn't matter which order you do those things in, whereas the quotient rule, that matters. So I definitely always be coming across here to check on my quotient rule formula. Okay, so my first function being 3x, I'm going to differentiate that first. I'm going to do it backwards to the formula sheet. So derivative of 3x is 3. We leave the second part of the function as it is, so that's going to stay as e to the 2x, plus we leave the first part of the function as it is, so that's 3x, multiplied by the derivative of the second part of the function, so derivative of e to the 2x. Again, if I'm not sure, I can go to my formula sheet. My rules for differentiating e to the ax, e to the ax are here. So it will be a e to the ax, so in this case that will be 2e to the 2x. So 2e to the 2x. Okay, so that's going to be 3e to the 2x plus 6x e to the 2x. Stop there, nothing wrong with that. Don't need to do anything further. Yes, you could factorise out a 3e to the 2x if you wanted, but it is completely not necessary to do so. And again, the more steps you do, the more opportunity you're giving yourself to make a mistake. So it could be written like that, but this would be a completely optional line. You would earn the 1 mark, probably even at the first line, to be honest. Find and simplify the rule of f dash of x, where f is this function here. So we've got a quotient, a cos function divided by an exponential function. So again, check your formula sheet, quotient rule, and your rules for differentiating cos and e to the x are all here. So there's no excuse for getting those things wrong. Get used to using the formula sheet and knowing what's there and what you can look up. So my quotient rule, because there's a subtraction on the numerator, that order is important. So I differentiate the numerator and I multiply it by the denominator first, and then I subtract, and I leave the numerator as it is, and I differentiate the denominator, and then I divide by the denominator squared. My derivative of cos x is negative sine x, I can see from up here. So making sure that we've got access to all those things that we need. Okay, so f dash of x, notation consistent with the question. So in the first question, the function was called y equals something. The derivative is dy dx. Don't call it something else. In the second part B here, the function is called f of x. Its derivative is f dash x, and the question's actually very explicit about what you should be calling those derivatives. So don't mix it up. Use notation consistent with the question. So f dash x, quotient rule. So we differentiate the numerator. So derivative of cos is negative sine. We multiply by the denominator, leaving that as it is. We subtract, we leave the numerator as it is, and we multiply by the derivative of the denominator, and the derivative of e to the x is just e to the x. All divided by e to the x, all squared, which, yes, we can write as e to the 2x. I'll do that in a minute. Now, there is a bit of simplifying to do here, and it's interesting. It would be interesting to know, I didn't mark last year as to how this might have been marked, but I do think this is not in simplest form to stay at this point. You'd earn your 1 mark here for having used the quotient rule. I've got a common factor of e to the x, in fact negative e to the x on the numerator, so negative e to the x, and then I've got sine of x plus cos of x, and on the denominator, on the denominator I've got e to the 2x. Now this e to the x and e to the 2x, they're going to simplify. So e to the x on e to the 2x, subtracting powers, that's e to the x minus 2x, so that's e to the negative x, or it means we just keep an e to the x on the denominator. So we're going to have negative sine of x plus cos of x. Now again, you might not have that negative factored out, that's fine, over e to the x. It did say find and simplify, so yes, you would definitely be expected to cancel down that common factor of e to the power of x. Okay, question 2, usually an antiderivative or fairly straightforward integral question. So find the rule for an antiderivative of g of x. Okay, so this an is important. My apologies, my washing machine's going, I hope you can't hear that. And meaning that if you omit the plus c, there's no issue with that because c could be 0 and that would be an example of an antiderivative. So it's actually a nice bit of lenience there. So we're looking at antidifferentiating g of x. So antiderivative of g of x with respect to x, don't forget your dx, that's still important. So that is the antiderivative of 3 on 2x minus 3 dx. Now, this is going to be a log, the antiderivative of 1 on x, and this is just a variation of 1 on x. The formula sheet's not very helpful with the log antiderivatives. It literally just gives you the 1 on x, okay? Oh, sorry, another one. It literally just gives you the 1 on x, it's the one above, rather than giving you an example for 1 on ax plus b. It's interesting how they do variations where sometimes the formulas on the sheet are quite helpful and sometimes they're really quite limited, and the log one is an example of that. So this is not an example like this because this would be where n is not negative 1, and in our example we would have n is negative 1. So it's not that, it's a log. Now there's a number of different ways that we could anti-differentiate this. So I'd definitely be wanting to take that 3 out, but we could also, if we really wanted to, take out 3 on 2. So I'm going to do this a couple of different ways. We might decide to do this, and then it becomes 1 on x minus 3 on 2. Okay, and then my answer would become the 3 on 2 is just going to sit there. This is going to be log e of. Now, I might choose to use modulus signs. I actually don't need to because this domain qualifier up here is ensuring that it wouldn't matter if I didn't have the modulus signs, and that's how VCAA generally get around having removed modulus from the course. So it would be perfectly correct for these to be round brackets, but not incorrect for them to be modulus either. We don't need the plus c because of the n. Okay, so again, I don't think you'd be marked incorrect for putting the plus c, but the an antiderivative, you also wouldn't be marked wrong if you chose to put plus 73 here. That would be an example of an antiderivative. Okay, so that might be what my answer looks like. Or if I didn't take out the 3 on 2, or I would have taken out the 3, but if I left the 2 inside the denominator, I might have also had, let me see if I can fit this in here. So we might have instead written this as 3 times 1 on antiderivative 1 on 2x minus 3, in which case my 3 would still sit there. It would be log e of 2x minus 3, but I'd also have to divide by this 2, this coefficient of x. So we'd have half log e of 2x minus 3, which would mean my answer would be 3 on 2 log e of 2x minus 3. Okay, and these are both correct and the same answer. They just have a different c value. There's just a common factor of 2 in there. And because of the way log laws work, when we multiply inside the log, it becomes addition. That's actually just an added constant. That's the difference between those two things. So either of those would be perfectly correct answers to that question. Okay, so part B. Evaluate this, where this is, and this. Okay, so we've got quite a lot of information here. So we want to focus on what it is that we're trying to evaluate, but we've also got some information that's going to be of use to us. We've got what the antiderivative of f of x squared is when integrated from 0 to 1, and we've got the integral of f of x from 0 to 1 as well. So let's focus on what it is that we're trying to work out and see how we can make use of these two things here. So we want to be able to identify or isolate out of the thing that we're trying to calculate these two things, so we can replace them with 1/5 and 1/3. So we're integrating from 0 to 1, and it is f of x times 2 times f of x minus 3. So if I expand out those brackets in that integral, f of x times 2 times f of x, that's 2 times, sorry, I'll write that. That's 2 times f of x squared, which is where this yellow highlight value is going to come in handy, minus 3 times f of x dx. Don't forget your dx's. Okay, so we could split up this integral. So this is 0 to 1 of 2 times f of x squared with respect to x minus 0 to 1 of 3 times f of x dx. And our properties of integrals allow us to take those constants out. So we're going to have 2 times the integral from 0 to 1 of f of x squared dx minus 3 times the integral from 0 to 1 of f of x dx. Okay, and so now I have actually isolated those yellow and green expressions. So this is the yellow thing, we know that equals 1/5, and this is the green thing, and we know that that equals 1/3. So we can now make those substitutions. So we're going to have 2 times 1/5 minus 3 times 1/3. Okay, so that is 2/5 take away 1. 1 is 5/5. 2/5 take away 5/5 is negative 3/5. Okay, now some students might have been thrown by the fact that the answer here was negative, but there was no suggestion here that this integral represented an area, so there's no need to make that value positive. It is perfectly possible for integrals to give a negative answer. If they are an integral to represent an area, you've set up the wrong integral, but it's perfectly possible to evaluate an integral and get a negative value, okay? So there's nothing wrong with that value being negative, but I suspect that could have thrown some students who then just made that answer positive. Okay, question 3. Now this is where I'm going to be looking at this question with a 2023 lens. So in 2022, I would have taught my students to answer this question by setting this up as a matrix equation and looking at when the determinant of the 2 by 2 matrix is 0. But that is no longer, matrices are no longer part of the 2023 course, and yet these kind of questions remain part of the course. I sort of thought they'd become a bit sidelined, but VCAA have certainly put them out as part of their sample questions, and it seems to be very apparent that they intend to continue asking this, which, to be honest, I think is a bit frustrating given that they've justified the additions to the study design by removing all of the content related to linear and quadratic functions and just stating that that's assumed knowledge. And here we are explicitly testing linear functions. Anyway, so we've got two linear graphs here with unknown coefficients involving k. And so we're looking at the value of k so that this system of equations has an infinite number of solutions. Okay, so if these are linear graphs, okay, and so there are 3 possibilities of what can happen when we're looking at simultaneously solving 2 linear graphs. They could be 2 linear graphs that cross over at a point, and therefore the solution of the simultaneous equations will have one solution. We will get a point that is the point of intersection between those 2 lines. We could have 2 parallel lines, in which case those lines would have no points of intersection and the system of simultaneous equations would have no solutions. Or it could be the case that the 2 lines are actually the same line, so they therefore have infinitely many solutions. So the parallel and same line both have the property that the gradients have to be the same. The same line one, we also need to have the same y-intercept, but the parallel lines, obviously we would need same gradient but different y-intercept. Where the 2 lines intersect, we're going to need different gradients. The minute the 2 lines have a different gradient, they're going to intersect. So we're interested in this third case here where they're going to actually be the same line, which means we're going to need same gradient and same y-intercept. Now, we can do this in slightly different ways, but I think to make it clearer as to what's happening is I would therefore rearrange both equations into y equals mx plus c form, so gradient intercept form, so make y the subject, so that I can see what the gradient of each line is and what the y-intercept of each line is, and then I can make the relevant equations. So my first equation is kx minus 5y equals 4 plus k. So I want to make y the subject here. I'm going to try and keep things positive, so I'm going to think about adding 5y and taking away 4 and k. So I'm essentially going to get kx minus k minus 4 equals 5y. Just keeps things a bit more positive. And then I need to divide everything by 5, and I'm also just going to rewrite it on the other side. So we're going to have k on 5 times x minus k on 5 minus 4 on 5. Now, I could have written that division by 5 in lots of different ways. I could have written the whole thing over 5, etc. But I do want to be able to identify the gradient, which is the coefficient of x, which is going to be that value, and the y-intercept, which is going to be that value. Let's rearrange the second equation, and then we can equate gradients and equate y-intercepts. So our second equation is 3x plus k plus 8y equals negative 1. So I'm going to have k plus 8y, making y the subject, equals negative 3x minus 1. I'm going to divide by k plus 8, so that is negative 3 on k plus 8 times x, minus 1 on k plus, 1 on k plus 8. Okay, so here in my second equation, there's my gradient, and there is my y-intercept. Okay, so we need same gradient, which means that k on 5 has to be equal to negative 3 over k on 8. And we want to solve this equation for k. So I'm going to multiply by k on 8, and I'm also going to multiply by 5. So multiplying both sides by k on 8 and multiplying both sides by 5 gives me this. K squared plus 8k equals negative 15. And so k squared plus 8k plus 15 equals 0. And that factorizes, so that is k plus 3 times k plus 5. And so therefore k equals negative 3 or negative 5. So those are the two values of k that give the two lines the same gradient. So it's possible that only one of these values of k also gives us the situation where we have the same y-intercept, and so that's where we also need to consider the two y-intercepts. So same gradient was us equating the two yellow things. Same y-intercept is going to be us equating the two green things. So that's going to be negative k on 5 minus 4 on 5 equals negative 1 on k plus 8. Everything here is negative, so let's get rid of all those negatives. K on 5 plus 4 on 5 equals positive 1 on k plus 8. Sorry, the washing machine's really going for it now. Okay, and so we might have this written as k plus 4 all over 5. We might have done that earlier, but I was a bit careful about this back here. It would have been easy to accidentally have this, I'm pointing up here, sorry, to have had this expression up here written not quite correctly with the negative wrong if I'd written it as one single fraction, so I think it was safer just to divide each thing by 5. So it's 1 over k plus 8. Alright, multiplying both sides by k plus 8 and both sides by 5, I'm going to get k plus 4 times k plus 8 equals 5. Expanding out the left-hand side, so k squared plus 12k plus 32 equals 5. Subtracting 5, k squared plus 12k plus 27 equals 0. Factors of 27 that add up to 12, that'll be 9 and 3. So we're going to have k plus 3 and k plus 9. And so therefore, we have the same y-intercept when k equals negative 3 and when k equals, negative 9. Okay, so we need both of these things to be true. So we need to have same gradient and same y-intercept, and so therefore we need the intersection of these two things, which is clearly going to be k equals negative 3. So therefore k equals negative 3 gives same gradient and same y-intercept, which implies that we have, sorry, I've got a bit of a lag, which implies that we have the same line, which implies that we have infinitely many solutions. So this would be my answer. K equals -3. Okay, and question 4. So we're into some probability. So a card is drawn from a deck of red and blue cards. After verifying the color, the card is replaced in the deck. This is performed 4 times. Each card has a probability of 1/2 of being red and a probability of 1/2 of being blue. The color of any drawn card is independent of the color of any other drawn card. Let X be a random variable describing the number of blue cards drawn from the deck in any order. Okay, so X is actually a binomial variable. It's either blue or it isn't blue. The probability of it being blue is 1/2, and the value of n is 4. We're doing this 4 times. So therefore, to work out this is the probability that X equals 1, which means that that is 4 choose 1. Sorry, I lost my train of thought for a minute. 1/2 to the power of 1 and 1/2 to the power of 4 minus 1, which is 3. 4 choose 1 is 4. 1/2 to the power of 1 is obviously 1/2, and 1/2 to the power of 3 is 1/8. And so that's going to be 2 times 1/8. That's me just doing 4 times 1/2, and then that's 2/8, which is 1/4. So this value here is going to be 1/4. Now you'll notice that they've left this as 6/16, which I don't really love. I think that should definitely have been given as 3/8. But I think they're trying to help you to be able to add everything up to 1 here. And therefore, in fact, looking at the examiner's report, they've given this value as 4/16, which I think would have also been correct, but certainly you're not going to be penalised for giving them the answer as 1/4. Now, the other thing to recognise here, there are a lot of ways that you could do this more efficiently. We could obviously repeat that process using our binomial formula for x equals 3 and for x equals 4. But what we also want to be able to recognise is the symmetry that we have going on here. So because the probability of success is 1/2, these probabilities are going to be symmetric. And so therefore, we can just repeat that this will be 1/4 and this will be 1/16. So we don't need to do any further calculations. The other thing we could have recognised if we'd recognised the symmetry straight away is that we could have seen that these two things were going to be the same, added everything up to 1 and solved that for x and got, 4/16 or 1/4 in that square there. So either way, however you went about doing it, this should be 1/4, this should be 1/4. As I said, the examiner's report says 4/16 there, so that would certainly have been marked correctly, although as a general rule I would say fractions should always be given in simplest form, so I'd be very cautious about giving an unsimplified fraction as your answer. Part B, given that the first card drawn is blue, find the probability that exactly 2 of the next 3 cards drawn will be red. Okay, so this is technically a conditional probability, but actually you don't need to calculate it as a conditional probability. Now there's not really enough space here for me to draw a tree diagram. I'm just going to scroll up to the inside cover sheet which had some space on it and just draw a tree diagram there to show you what I mean. So we're drawing 4 cards, they're either red or blue. Given that the first card is blue, find the probability that exactly 2 of the next 3 cards drawn will be red. So let me just scroll up to where there was a blank inside cover here. Yeah. Okay, so 4 cards, red or blue. Sorry, I should have done that wider to start with. It's the key to a successful tree diagram. Start wide, red and blue, red and blue, alright, and then our 4th one, red, blue, red, blue, red, blue, red, blue, red, blue, red, blue, and red, blue. 2 more, sorry. Okay, so given that the first card drawn was blue, means it's telling you that we are starting at this point. So actually, from the tree diagram, the only bit of the tree diagram that's relevant is this. Okay, And then we don't actually need to calculate a conditional probability. We don't need to calculate the probability of blue, red, red, blue, blue, and then divide by the probability of blue at the first stage. We're just omitting having to think about this probability at all by just starting the tree diagram here. So given that the first card was blue, what is the probability that it's red from then on? So we actually only need to essentially start from here. So we want, I think it was it 2 reds? Sorry. Given the first card drawn is blue, find the probability that exactly 2 of the next 3 cards drawn will be red. Okay, so exactly 2 of the next 3 cards drawn will be red. So that therefore is going to be this branch, this branch, this branch, and that's it. Okay. Everything's a half here, so these things are all just going to be just half times half times half, and okay, so this is going to be, this probability is 1/8, this probability is 1/8, and this probability is 1/8, and we add those up, and so we're going to get 3/8. So it's essentially just the probability of getting 2 reds when you choose 3 cards. Okay, so you're essentially ignoring the first card. We could have done the whole thing, and if we'd done the whole thing, then the probability of getting a blue and then 3 reds would have been 1/16 and 1/16 and 1/16, because we would have done the 1/2 from here, 1/2, 1/2, 1/2, but then we would have had to divide by the probability of getting a blue at the first thing. So what I'm saying is probability of blue first, sorry, other way around, probability of 2 red, this is a very loose description, because it's not just any 2 red, it's 2 red from the last 3. So probability of 2 red given blue first would technically be the probability of getting 2 reds and blue first, okay, over the probability of blue first. So what I'm saying is that numerator probability would have been 3/16 over 1/2, which means 3/16 times 2, which means 3/8. So you actually just don't even need to factor that thing in. That's what conditional probability is doing. It's reducing your sample space. It's allowing you to start your tree diagram from this point here. Whatever else happens you're not interested in. So we can literally just not worry about this bit at all. And then these probabilities here become 8s. So it's 1/8 plus 1/8 plus 1/8, so 3/8. Alright, I think this is just a 1 mark question, so I probably would have had a little tree diagram drawn down here. The other thing to recognise is it is just, it's also just a binomial probability. It's the probability of getting 2 reds from 3 selections. So therefore that would be 3 choose 2, half to the power of 2, half to the power of 1, which is still going to give us 3/8. So probability of 2 red given that the first card is blue. So it's just a 1 mark question, so I'd have drawn a rough tree diagram here, or recognise, as I said, that this is 3 choose 2, half to the power of 2, half to the power of 1, which is going to get you to the 3/8. The deck is changed so that the probability of a card being red is 2/3 and the probability of a card being blue is 1/3. Given that the first card drawn is blue, find the probability that exactly 2 of the next 3 cards drawn will be red. Okay, so we've already done the thinking through of what we need to worry about. So I'm probably going to use this formula here, but I could also go back to my tree diagram and adjust my tree diagram. So this would be, again, probability of 2 red given first card is blue is just going to be, where the first card being blue is assumed and it's done, and we're starting our tree diagram from that point, and so therefore from the next 3 cards we need 2 of those to be red. Okay, so that means 3 choose 2, the probability of a red, which is 2/3 to the power of 2, times the probability of a blue, which is 1/3 to the power of 1. 3 choose 2 is 3, 2/3 squared is 4/9 times 1/3. So that 1/3 and that 3 are going to cancel out, and so we just get 4/9. So again, you could go back to your tree diagram and edit it. Actually, there's good space at the bottom here to have drawn a tree diagram and edit the probabilities. And essentially, you've still got those same 3 branches. Each of those 3 branches have 2 branches with the 2/3 on them and 1 branch with a 1/3 on them, which is exactly what this formula here is calculating for us. Okay, question 5. Solve 10 to the power of 3x minus 13 equals 100. So this is a really straightforward exponential equation. Teach these with my Year 10 class. So we want to, the easiest way to solve exponential equations is if we can write both sides of the equation with the same base, that's what we'll do. So in this case we can do that, we don't need any logs. So this is 10 to the power of 3x minus 13, 100 is 10 squared. And if we can write both sides as a single exponential with the same base, then we can simply equate the powers. So 3x minus 13 equals 2, and therefore 3x equals 15, and therefore x is equal to 5. Okay, part B, find the maximal domain of f where f of x is log e of x squared minus 2x minus 3. Okay, so this is a composite function. So we need the range of the inside function, so that is the range of the parabola, needs to be a subset of the domain of the outside function. That is the domain of the log. Okay, so we've essentially got 2 functions. We've got, let's call them, I don't know, g and h. So let's say this is g of h of x. So we're essentially saying that g of x is log e of x, which means that the domain of g is r plus, or 0 to infinity, and h of x is x squared minus 2x minus 3. And so we're going to need the range of h to be a subset of the domain of g, which means the range of h has to be positive real numbers only. So let's think about what h looks like. So h is a quadratic, that will factorize, x minus 3x plus 1. Okay, so it's got x-intercepts at 3 and negative 1. And it's a happy parabola, so that's what it's going to look like. So we need the range of h to be a subset of the domain of g, which means we need the range of h to be a subset of the positive real numbers, which means the range can't include these x-intercepts, and it can only include these bits up here and here. Okay, and so that's going to happen when x is less than negative 1, or when x is bigger than 3. Be careful about what you write here. Don't write and would mean the intersection, and there is no intersection between those two things. So in order for, we know that the domain of the composite function is the domain of the inside function, but in order for, so the domain of h, but in order for the composite function to exist, we needed to make sure that this subset, the range of h is a subset of the domain of g, so that the output from h can then become the input for g. Okay, so we know the domain of f is the domain of h, but in order for the composition to exist, that domain is going to have to be negative infinity to negative 1, not inclusive of negative 1, union 3 to infinity. And that would be our answer. Okay, question 6. The graph of y equals f of x, where f is a trig function, is shown below. So we've got domain of 0 to 2 pi, we've got the rule of 2 times sine of 2x minus 1, so an amplitude of 2 as caused by that. We've got a period of 2 pi on 2, so a period of pi. We can see that. We're seeing 2 complete periods happening between 0 and 2 pi, and down by 1. We're also seeing that. So the graph is drawn for us. On the axes above, draw the graph of y equals g of x, where g of x is the reflection of f of x in the horizontal axis. Okay, so we just need to reflect it. So this point at 0, negative 1 goes to 0, positive 1. This sort of turning point that looks like it's at, what's that, pi on 4, 1 is now at pi on 4, negative 1. The x-intercepts, they won't change. So this turning point here is going to come up to here. This x-intercept's not going to change. This turning point here is going to come down to here. Again, we can move some of these other points, so it goes through here and here, goes through here, and it's going to end there, and that turning point's going to be up there. Okay, so we've got literally just reflected a whole lot of points, so we're going to get a nice accurate graph. These days, now that VCAA give you, I missed that point, draw it a bit at a time so I can rub it out if I need. Now that VCAA usually give you full grids like this, it's really important that your graphs are drawn accurately on these grids. So, calculate extra points, mark extra points. It should actually go through these same key points. It didn't say that we needed to label anything. The original graph didn't have any labels. I think it's really just about the shape. Find all the values of k such that f of k equals 0 and k is between 0 and 2 pi. Okay, so we're really just finding the x-intercepts of those graphs. So f of k, you are solving for k though. I know it would be the same to solve f of x equals 0, but the answer asks for all values of k, so make sure your answer is k equals. Okay, so f of k is 2 times sine of 2k take away 1. We need that to equal 0. So we've got a trig equation to solve, so we get the sine part of the function on its own, add 1 and divide by 2. Then we need some exact values. So I'm going to call on my special triangles. Half of an equilateral triangle of side length 2, which makes that length 2 and that length 1. Pythagoras gives us that length is 3. I need sine to equal a half, which means this 1 must be the opposite side, opposite of hypotenuse. So 1 must be opposite, 2 must be hypotenuse, which means we must be talking about this angle up here, which is half of the 60-degree angle, so 30 degrees or pi on 6. We then need quadrants. We want our solutions for k to be between 0 and 2 pi. Okay, but we're originally not getting solutions for k. Our solution is going to equal 2k, which means those solutions need to be between 0 and 4 pi. So we've got pi on 6, sine is positive, so we're in the two quadrants where sine is positive, which is quadrants 1 and 2, and we're going to go from 0 around to 2 pi, and then we're going to need to go around again to 4 pi to get all of the solutions in the domain. So there is going to be 4 solutions, 2 full laps of the circle. So that first solution is pi on 6. That next solution is pi minus pi on 6, which is 5 pi on 6. The next solution is 2 pi plus pi on 6, so 2 pi is 12 pi on 6, plus another pi on 6 is 13 pi on 6, and 3 pi minus pi on 6, so 3 pi is 18 pi on 6, and so minus 1 is 17 pi on 6. Okay, now we can divide everything by 2, which means that all of these denominators are going to become 12. So pi on 12, 5 pi on 12, 13 pi on 12, and 17 pi on 12. Now 24 pi on 12 would be 2 pi, and so we're definitely within our domain. Last year's examiner's report made mention of the need to have a way to know your exact values. That really is why I advocate the special triangles. I'm not remembering them, I'm able to generate them. It's not a memory thing, I'm certain that I've got it correct. I know that if I have an equilateral triangle, all these angles will be 60 degrees or pi on 3, and if I cut that in half, I create a right-angled triangle with an angle of 30 degrees, which is pi on 6, and 60 degrees, which is pi on 3. I could make the side lengths of that equilateral triangle whatever I want. If this was 10, then this would be 5, and this would end up being 5 root 3. So the ratios would still work out the same. If I needed sine to be a half, that would have to be 5 on 10, which gives me a half, so it's still about pi on 6. So the simplest numbers to use obviously make the side length of the equilateral triangle 2, then this is 1, then this is root 3. Equally, you could also make the hypotenuse 1, which would make this half and this root 3 on 2. Okay, and again, it's still going to work. Sine of pi on 6 is a half over 1, so I'm just using my right-angled trig, SOHCAHTOA. Go back and have a look at some of my circular functions videos, particularly the one about exact values if you need to learn how to remember your exact values. Just trying to rote learn them or remember a table, you have no way of knowing that you've remembered the correct value. You're literally just guessing in the exam. Okay, part C. Let H be... H of x has the same rule as f of x with a different domain. Okay, so our rule is the same, but our domain is now different. So it's the same function that we've got a picture of up here, the original graph, not the one that I drew. Okay, but we're going to change the domain of it. The graph of y equals h of x is translated a units in the positive horizontal direction and b units in the positive vertical direction so that it is mapped onto the graph of y equals g of x, where a and b are positive. Okay, so A and B are both positive, which means if we go A units in the positive horizontal direction, we are definitely going to the right, and B units in the positive vertical direction, we're definitely going up. So we're going right by A and up by B, and we need to turn h of x, which has the same rule as f, into g of x, which is the graph we drew up here. Okay, so this one I drew is y equals g of x. Let me see if I can change the colour of that easily so we can sort of see that a bit more clearly. Yep. Let me make that blue instead. Okay, so g of x is the blue graph, and f of x is the black graph. So and f of x is also the same as h of x, but we're potentially going to change the domain of h of x. But for now, let's treat it as h of x. So we want to, by translating to the right and up, turn the graph of h into the graph of g. So looking at this, just pick a key point wherever it is. I'm going to think about this point here that is currently at pi on 4, 1. And I'm going to need to move that across and up. So it ends up here at, so it looks like that's at 3 pi on 4, 3. So we clearly have to go across by 2 pi on 4, which is pi on 2. And we clearly have to go up by 2 in order to get the same graph. And you can check that it should be the same whichever 2 points you take to apply those transformations. Okay, so we need to go right by pi on 2 and up by 2. So find the value for B. So the value for B is the up value. Okay, so B is going to be 2. Sorry, just changing my pen color. It's a 1 mark question, so I can just state that. Find the smallest positive value for A. Okay, so A is going to be pi on 2. Now, it asks for smallest positive value for A, and that's because it's a trig function, we could also have chosen to go all the way across to here and up by 2, and it still would have given us the same graph. So the smallest one is simply to go to take the first turning point to the next closest turning point, which is what we've done. So A is going to be pi on 2. Okay, so then, hence or otherwise state the domain D of h of x. Okay, so this was fairly poorly done last year, but this is where we've got to understand that our original function f of x had a domain from 0 to 2 pi. So if we had, now let me just rub out those annotations so you can see what I'm doing. So if I had literally taken the graph of f and done these 2 transformations to it, sorry, I'm just trying to get rid of, so this original black graph, this point, we move it to the right by pi on 2 and up by 3. Oh, sorry, where am I? Up by 2, sorry, right by pi on 2 and up by 2. It would have ended up here. Right, we would have ended up here, etc., etc. This endpoint here, we move that to the right by pi on 2 and up by 2. And that's going to end up here. Okay, so what happens here is this here is the graph that we end up with. So this, we're following the same shape, but the domain's now not right, okay? Because the domain is starting here at pi on 2 and it's finishing here at 2 pi plus pi on 2. So we actually want to be able to transform h of x, translate h of x, so that we literally end up with g of x. We literally end up with that bit of the blue graph that is between 0 and 2 pi. Which means in order to do that, we needed this bit back here as well. Okay, so we actually needed, and we didn't need, this bit here. Okay, so we actually need the domain of the original function, h of x, which has the same rule as f, but has a different domain. We needed that original domain to go from negative pi on 2 back here to pi plus pi on 2, so 3 pi on 2 here, so that when we take that chunk of the graph, that piece of the graph, and move it to the right by pi on 2 and up by 3, we get exactly the blue graph, not the red graph. So we want the blue graph, we want it to end up between 0 and 2 pi. Okay, so therefore our original domain of this function needed to be from negative pi on 2 to 3 pi on 2, so that then when we translated it right by pi on 2 and up by 2, sorry, I think I keep saying up by 3, and up by 2, we end up with that exact picture of the blue graph sitting between 0 and 2 pi. Okay, question 7. A tile maker wants to make square tiles of size 20 centimeters by 20 centimeters. The front surface of the tiles is to be painted with 2 different colors that meet the following conditions. Condition 1, each color covers half of the front surface of the tile. Okay, so for each tile, the gray area has to be the same as the white area. And condition 2, the tiles can be lined up in a single horizontal row so that the colors form a continuous pattern. Okay, so that means that they're going to need to join for these to be continuous, so at these endpoints. There are 2 types of tile, type A and type B. So we can see from the graph that there are different tiles. There are ones where the curve goes this way and then ones where the curve goes this way. Okay, so let's see what it tells us. For type A, so type A looks like it is like the first one. This one is a type A. Okay. This one's a type A and this one's a type A. So type A, the colours on the tiles are divided using the rule f of x equals 4 sine of pi x on 10 plus a, where x is an element of R. The corners of each tile have the coordinates 0, 0, 20, 0, 20, 20, and 0, 20. Okay, so we've essentially got the axes happening here. This is our curve, y equals 4 sine of pi x on 10 plus a. Find the area of the front surface of each tile. Okay, so the tiles are clearly 20 by 20. And so the area is simply, it's a 20 by 20 square, so 20 by 20. And so it's going to be 400, what are our units? Centimeters. 400 centimeters squared. Okay, so find the value of A so that the type A tile meets condition 1. Okay, so condition 1 is about the fact that the grey and white areas need to be the same. So because we have a sine function, and because we can see that the period of this sine function is 2 pi divided by pi on 10, which is 2 pi times 10 on pi. The pi's cancel and we get 2 times 10, which is 20. So the period is 20, so that means this is at one complete period of a sine graph. And so everything is nice and symmetric, which means that this starting point and this ending point are going to be exactly the same, which means that this bit of area here is going to be exactly the same as this bit of area here. And so really all we need to know about A is it's literally just going to be the translation up by A. Okay, and then because we've got a full period there, that's going to make sure that the curve splits the tile in half. So obviously we need to go up by half of the height of the tile, so we're going to need to go up by 10, and so A is going to have to be 10. It's just a 1 mark, find the value of A, so we can just state that A is 10. Type B tiles, an example of which is shown below, are divided using this rule. So we have a cubic rule. Show that type B tile meets condition 1. Okay, so we're going to need to show that the area under this curve is half of the area of the tile. Okay, so let's set up an integral to work out this shaded area. So it's going to be integral from 0 to 20 of our function, which is negative 1 on 100 x cubed plus 3 on 10 x squared minus 2x plus 10 dx. Alright, we need to evaluate that. It's a show that, so we need to do it. We don't have our cas, so we need to do it. So x to the power of 3, we add 1 to that power, x to the 4, divide by that power. So it's going to become negative 1 on 400, x to the power of 4, plus add 1 to the power gives me 3, and dividing by 3 will give me 1/10 rather than 3/10, x to the power of 3, minus 2x squared on 2, so that's going to be x squared plus 10x. And we want to go from 0 to 20. Okay, so that means we're going to have negative 20 to the power of 4 on 400 plus 20 cubed on 100, sorry, on 10, minus 20 squared plus 10 times 20. And when we substitute 0 into that, we're going to get 0, 0, 0, 0. Do always think about the substitution of 0. Because this is a polynomial, subbing 0 in will give us 0. But, you know, exponentials, when you substitute e to the 0 is not 0, cos of 0 is not 0. So do make sure you always consciously think about that 0 substitution. Okay, so 20 to the power of 4. All right, let me think that through. 2 to the power of 4 is 16. Okay, so I'm essentially doing 20 times 20 times 20 times 20. And what I've essentially done is I've thought about that as being 2 times 2 times 2 times 2 times 10 times 10 times 10 times 10. It's essentially how I'm doing it in my head. So that bit will be 10 with 4 zeros on the end of it. And this bit was 16. And so therefore we're going to have 160,000 over 400. So you do need to be able to do this level of number work. We've had some fraction work, we've had some number work, we've had to factorise quadratics, we've had to use all our basic skills here. 20 cubed, so 2 cubed is 8, and 10 cubed is 1,000, so it'll be 8,000 over 10 minus 20 squared we've just done before is 400, plus 10 times 20 is 200, and minus 0. Okay, so these zeros are going to cancel down. 1,600 divided by 4 is 400, so that's negative 400. 8,000 divided by 10 is 800, minus 400 plus 200. Okay, so I've got minus 400 and minus 400, which is minus 800 plus 800. So that those first three terms all cancel out to give 0, and so we're just going to have 200. Now, this was a really interesting question they made a really good point about in the examiner's report. So what we're being asked to do is not calculate the shaded area. We're being asked to show that a type B tile meets condition 1, which means we need to show that the shaded area is half of the total area of the tile. So you need to actually bring that together to have fully answered this question. Okay, so 200 is half times 400, which is half times the area of the tile. Okay, or maybe at the beginning you said that the area of the tile is 400 centimeters squared, and so therefore the shaded area needs to be 200 centimeters squared, and then calculated the shaded area. Don't start by writing that it equals 200. You're showing that it equals 200. Work it out, and when it equals 200, draw a conclusion about what that tells you. But it was really important that you actually had to bring it together at the end. So I suspect mark-wise, a mark for setting up the integral, a mark for getting it to equal 200, but a mark for bringing it together in terms of what it shows in terms of it meeting condition 1. Okay, so again, I haven't even mentioned condition 1, so I think that should be part of my answer. Show that type B tile meets condition 1, so we found that the shaded area is 200. 200 is half of 400, which is therefore half of the area of the tile, and so therefore type B meets condition 1. Okay, so make sure that you actually explicitly reference the thing you're being asked to show in the question. Show that it meets condition 1, therefore make sure that there's a statement about that in your answer. Determine the endpoints of f of x and g of x on each tile, hence use these values to confirm that type A and type B tiles can be placed in any order to produce a continuous pattern in order to meet condition 2. Okay, so remember condition 2 was about the fact that the tiles could be lined up in a single horizontal row so that the colours form a continuous pattern. So they don't need to meet smoothly, but they need to meet. So we need to make sure, therefore, that the endpoints of both tiles meet at the same point. So we're going to need to know f is type A, so we're going to need to know f at 0 and f at 20, and g is type B, we're going to need to know g at 0 and g at 20, and confirm that those are the same things. So let's just work out what we've got here. So type A, the function was f of x equals, sorry, I've forgotten again, 4 sine pi x on 10 plus 10. Okay, so f at 0 is 4 sine of 0 plus 10. Now sine of 0 is 0, so that is just 10. F at 20, so on the other side of the tile, is 4 sine of 20 on 10, so that'll be 2 pi plus 10. Sine of 2 pi is also 0, and so that is 10. Let's think about type B. Our rule was up at the top of this page. So g of x is negative 1 on 100x cubed plus 3 on 10x squared I think it was minus 2x plus 10. Sorry. Okay, so g of 0 is just going to be 10, obviously. 0 plus 0 minus 0 plus 10. And g of 20 is going to be a bit uglier, but we've done some of this calculation already. So 20 cubed was 8,000, so it's going to be negative 8,000 on 100. So that's going to be 80. Plus 20 squared was 400, so it's going to be 1,200. Oops, sorry, not 12,000. 1,200 on 10. It's going to be 120. Minus 2 times 20, which is 40, and plus 10. So that is negative 80 plus 12. Sorry, not 12. 120 minus 40 and plus 10. So the negative 80 and the negative 40 are negative 120, so they cancel with the positive 120, and so therefore we just get 10. Okay, so again, we need to make a conclusion from this. So determine the endpoints of f of x and g of x on each tile. So we've done that. Hence, use these values to confirm that type A and type B tiles can be placed in any order to produce a continuous pattern in order to meet condition 2. So sorry, I'm just trying to think how best to phrase it. Perhaps the boundary between the white and coloured areas of both tiles is at a height, sorry, what a lag, height of 10 centimetres at both edges, meaning that the tiles can be lined up in any order just trying to, let me just check what the wording was in condition 2. So the colours form a continued pattern, any order, so that the colours form a continuous pattern. Hence, oops, the tiles meet condition 2. Okay, alright, question 8. I think question 8 is the last question on the paper. Part of the graph of y equals f of x is shown below. The rule a of k equals k sine k gives the area bounded by the graph of f, the horizontal x-axis, and the line x equals k. Okay, so what we've learnt here is that the integral from 0 to k of f of x is a of k. Okay, it is k sine k. So that's what the statement is telling us. This is that area, and we know that area could be represented by this integral, and so therefore those two things are the same thing. Okay, state the value of a of pi on 3. So therefore we're working out what the shaded area is when x is pi on 3. So it's just a simple substitution. So a of pi on 3 is therefore going to be pi on 3 sine of pi on 3. Sorry, when k is pi on 3, but it's the same thing because k equals x. Again, we need to know our exact values. This is the second time in the tech-free paper we've needed to know our exact values. So our half equilateral triangle that we talked about earlier, sine of pi on 3, so that's 60 degrees, that's pi on 3 down there. Sine of pi on 3 opposite over hypotenuse, sorry I put that 2 in the one around the wrong way. The side length of the equilateral triangle is 2, which will be that length, and therefore that's half of that length. So sine of pi on 3 opposite of hypotenuse will be root 3 on 2, and so therefore this is going to be pi on 3 times root 3 on 2, so pi root 3 over 6. Evaluate f at pi on 3. Okay, so what we're working out here is if this value here were pi on 3, that is the shaded area, and then when we do f at pi on 3, we're working out the y coordinate of this point up here. Okay, so f at pi on 3. Now, we don't actually know what f of x is, but if we go back to this statement that I made up here about the fact that we know have a connection between a and f in terms of an integral, then the flip side of that is that the derivative of a is going to be f. If the antiderivative of f is a, then the derivative of a will be f. Okay, so we know that the derivative of a of k is going to be, actually let me write that the other way around. We know that f at k is going to be the derivative of a at k, which means it is the derivative, with respect to k, of k sine of k. Okay, so careful about the k's here. K isn't a constant. That's what we're differentiating with respect to. So we actually have a product rule here in terms of derivative. We've got k times sine of k. So differentiating k is 1. We leave sine of k as it is. Plus, we leave k as it is, and we differentiate sine of k, which is going to be cos of k. Alright, so we've got sine of k plus k cos of k is f of x, or f of k. And therefore f at pi on 3 is going to be sine at pi on 3 plus pi on 3 times cos at pi on 3. So again, third time, we need our exact values. I've got my triangle drawn up here. Sine at pi on 3 is root 3 on 2, and cos at pi on 3 is adjacent of hypotenuse, so that's half. So root 3 on 2 plus pi on 3 times a half. So root 3 on 2 plus pi on 6. Now you could leave that as it is, that's perfectly fine as that. You could get a common denominator if you want, which would mean multiplying this first fraction by 3. But either of those would be perfectly correct answers to that question. Okay, and then part C, which is the last question of the paper, I think. Consider the average value of the function f over the interval 0 to k, where k is between 0 and 2. Find the value of k that results in the maximum average value. Okay, so first we need an expression for the average value. So it's the average value over this interval, so that's 1 on k minus 0, integral from 0 to k of f of x dx. Okay, so that's 1 on k. Now, this, the integral from 0 to k of f of x dx, we have an expression for that. We thought about that right back here at the beginning. That is a of k, or k times sine of k. Okay, so this is a of k, which means we've got 1 on k times k sine of k, and so therefore sine of k is the average value. Now k is somewhere between 0 and 2, so we want the maximum average value. Okay, so let's therefore think graphically about what this looks like. Oh, sorry. So obviously sine of k, so this is the k-axis rather than the x-axis. Sine of k, is a fairly standard sine graph, but we're only going from 0 to 2. Now, we know from 0, this would be 2 pi, 2 pi is like 6 point something. So actually we're not even looking at this. So half of pi on 2 wouldn't even be 2. So we're not even looking at, what we're saying here is if that's, 2 pi, and that's, sorry, I meant pi wouldn't even be 2. So pi is 3.14. So we're probably looking at roughly about 2/3 of that, which means we're going to go past this turning point, but we're probably going to be stopping somewhere at this point. So it'll be 2 sine of 2. But the key thing is to recognize that that's going to definitely be bigger than pi on 2, because pi is about 3.14, and so pi on 2 is going to be about 1.57. Okay, and so therefore 2 will be between those two things. And so therefore the maximum value, so this is A and this is K on this axis, so therefore the maximum value of A is that, and we want the value of K that results in this maximum average value. Sorry, that's not A, it's average value. So the maximum average value is this value here, and the value of K that produces that is this value here. Okay, so the maximum average value occurs when K equals pi on 2. It's only a 2-mark question, so I suspect the first mark would be for either, setting this up, but I think that's possibly not going far enough. I think you'd need to make the connection to A of K, and so therefore I think actually it would just be for working out that the average value is sine of K, and then the value of K that gives the maximum average value, given that K is between 0 and 2. And that is the end of exam 1.